This is a recap of the lesson I did the last time we were together in class, and hoping that you find this helpful. So basically, I went through, on the next couple of slides, we're going to review linear work and then exponential work, and then we're going to go into the handout that I gave in class. So I want you to draw, or I had asked you in class to draw on your paper an X and Y table. And what I asked you to then do is fill in the table with the following. We have 0, 1, 2, and 3. I'm just going to go 0, 1, 2, 3. And we're going to fill in the Y side with the following numbers. We're going to go 5, and then 8, 11, and 14. And one of the things that I want you to note is, what are you noticing and wondering about this table? And I know oftentimes students will say, hey, Mrs. Hannaford, I noticed that the X values are going up by 1. Absolutely, that is correct. But in this case, when we go through these tables today, what I'd like you to do is be looking specifically at the Y values here. So what do you notice about the Y values? I'm hoping that you notice that they're getting bigger. Absolutely, I agree with that. And I'm going to ask you another question. How are they getting bigger? What pattern do you see them getting bigger by? And you know that because the numbers are getting bigger, that I can't be subtracting them. So you might go, well, what gives me numbers that are bigger? Either I can add them or I can multiply them. So I'm going to first look at adding. So what did I add to 5 to get to 8? Well, I added 3. So if I added 3 there, okay, well, will that pattern continue to hold for the rest of the numbers in that table on the Y side? So if I take 8 and add 3, I get 11. That's perfect. And when I take 11 and add 3, oh, I do indeed get 14. Awesome. So there we go. We've developed our pattern. What's our pattern? Our pattern is that I added 3 each time to my Y value, which is awesome, right? That's what we did each time. All right, so now what I'm going to do is I'm going to now just give you a quick sketch of a graph if I were to graph this. So again, I'm going to do my X and Y coordinate. I'm only going to use one quadrant because I don't have any negative numbers there. I'm just going to tick off some numbers along the bottom. And I know that this is 1, 2, right? This is 0 right here. This is 0. In fact, let me change that to red, like a red color, so you know. That's 0. And then I'm not going to mark anything on the Y side because my numbers range from 5 to 8 to 11 to 14. But, I mean, if I could do that. And give me a minute while I do that. So you can see that I actually went ahead and I ticked off. There's actually 15 little tick marks. So that means, again, this is 0 right there. And then I go 1, 2. All right. So I'm going to go ahead, and in class, I just did a quick sketch, but let's go ahead and let's actually graph each one of these points. So that means the very first point that I'm going to do is right here, 0, 5. I want you to remember that that's an ordered pair. So I'm going to go 0 on the X right here, and I'm going to go up 5. 1, 2, 3, 4, 5. So right here is my first point. And I'm going to erase this right here because I don't want us to get confused, right, with another. All right, so there you go. So that's my very first point. My next point is 1, 8. So that means I'm going to go on the 1 right here, and I'm going to go up to 8, right? All right, so what I did was I went to 1 on the X right here, 1 on the X. And then I counted up 8 dots. And notice I made little dots and then I made a big dot. And that's where the 8 sits. All right, I'm going to do the same thing with 2 and 11. All right, so you can see that I went on the 2 and then I counted up 11. And the last one that I'm going to do is 3, 14. So you can see that I put my third dot there. All right, so one of the things, again, like I said in class, I just did a quick sketch. But now look, if I connect these, this is a straight line. In other words, this is a linear function. How do I know it's linear? I'm adding 3 each time. Okay, this is constant. A constant rate of change. I'm adding 3 each time. So there you go right there. Again, reading a table, making sure I recognize a pattern. What was the pattern? I added 3 each time. And believe it or not, I could actually write an equation based on the fact that I know what my rate is. And I'm just going to give it to you right now that I would say that this equation is y is equal to 3x plus 5. So how did I know to do that? Well, this 3 right here is my rate that is happening. What did I do? I added 3 each time to the number. And then why did I know to start at 5? Well, right here, just like we've been learning about exponential graphs, this is my starting point. This is where my graph started on this, in this table. Right there, it started at 0, 5. So therefore, this is my starting point. All right, so that is linear work. All right, now, let's go ahead and let's talk about exponential work. I want you to draw a table again. So you can see I've built a table. I'm going to use the exact same numbers of 0, 1, 2, and 3. All right, this time my y values are going to be as follows. All right, so take a look. I said 5, 10, 20, 40, 80. And again, remember, we're looking only at the y values here. Because I know you're going to tell me, and you rightly so, that I added 1 to each number on the x side. Absolutely. Agree with you 100%. So now let's look at the y side. So remember, previously I said, okay, what did you do to 5 to get to 10? Well, you could say, hey, I added 5. Okay, perfect. I agree with you. But if I were to add 5, that means that I would have added 5 to get from 10 to 20. Well, if I take 10 and add 5, I get to 15. So that's not right. So I'm not adding. So then you could say, okay, well, I know I added 5 here. All right. And then I added 10 here. And then I added 20 here. Okay, yeah. That's true. I agree with you. But remember, we're looking for the same number each time. So what's another way that I can go from 5 to 10? What's another way I can go from 10 to 20? How could I go from 20 to 40? Well, I'm hoping that you noted that I can multiply by 2. Because 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. And 40 times 2 is 80. So notice this time, each time I had the number, I multiplied by 2. Well, that means I have got an exponential relationship. Exponential, that means it's multiplying right here. Exponential, if you think about what an exponent does, if I write 4 to the power of 3, this exponent tells me that I'm going to multiply 4 times 4 times 4. Okay, I'm multiplying. So that's why this is exponential, and my factor in this case is 2. All right, so now we're going to do a quick sketch. All right, again, x and y, just like before. And what else? Well, I know that I got 1, 2, 3, 4, 5, 6. I can keep going. This is 0 right there, right? And I'm not going to label the y-axis this time at all. But I know right here that I have to start at 0, 5. So wherever I go, if this is 0, I'm going to go up to 5. Let's just say this is 0, 5. Right here, this is 0, 5. Then that's where my graph starts, right here. This is where it starts. So I know it's doubling. I know it's exponential, which means it's going to be curved. This is an exponential graph. Okay, so one of the big takeaways that you need to realize with exponential growth is that we are growing by multiplying each time. This is what's different, and I'm going to go back one slide. In linear growth, we are adding each time. That's the huge difference. We are adding each time with linear, multiplying each time for exponential. So, to write an equation in a linear relationship, you need two things. You need to know what is the initial or starting value, just like in our graphs for lines. We also need to know the rate, the factor with which it's growing. And a factor means I'm multiplying. So based on this scenario right now, I can say that y is equal to, what is my initial or starting value? It's right here. It's 5. And I'm going to multiply that starting value by how did it grow? What did I multiply by each time? I multiplied by 2. And I'm going to raise that to the power of x. All right? So hopefully that helps with regards to understanding the difference between linear and exponential. And now on this next page is what we talked about in class about Diego understanding decay based on Diego having $100. Okay, so that's where we're going. This is the notes on the next two things. So we talked about what was left. So Diego has $100 and he spends 1/4 of it. How much does he have left? How could you figure this out? So I want you to note that this $100 is represented by this big block. And because you've got a fraction that says the denominator is 4, that means I'm going to cut this block up into 4 pieces. And if I say that I spend one of these blocks, this one block is 1/4. That's what this means. How much is left? How much means I have 3. Well, let me go in and say that this is 1/4, this is 1/4, and this is 1/4, right? I know it's 1/4 because I've cut the big block into 4ths. So this orange piece, how many 4ths do I have altogether? I have 3/4 left. So this is where all of this information right here comes from. Take a look. 3/4 is left. If I take 100 and I multiply that by 3/4, I would get $75. Take a look right here. I have 1 whole of something. 1 whole. Cut it into 4ths. 1/4, 1/4, 1/4, 1/4. I have one of them that I've taken away. What do I have left? 3/4. 100 times 3/4. Same exact thing. Okay, look at this one. 3/4 times 100. All we did was we flip-flopped, because I can do that in multiplication. Now let's go up to here. So what this means is we can take 1/4 of 100. 1/4 times 100. If you put that into the calculator, means I'm taking 1/4 of this. Means if this whole thing is, remember, cut it into 4th, I'm going to take 1/4 of that. Well, what is 1/4 of 1? 0.25. If I'm going to talk about it being 0.25 or $25, because I'm talking about $100. So this is 100 minus $25, which is equal to 75. This is equal to 75 if I were to use a calculator. 100 times 3/4. 100 times 3/4, 75. 3/4 times 100, 75. So we are looking at what is left. What is left? 3/4. All right, let's go ahead and now look at the situation about the car that I talked about in class. So now we're talking about bigger numbers, right? So here's a bigger number. We've got a car. And that car, after I purchase it, every year it loses 1/3 of its value. So we want to know, in order for me to answer these questions, we're going to figure out at the end of all of this, how much is the car losing each year? Right. So let me ask you this before I even get started. If it loses 1/3, what is remaining? What is left? Oh, I didn't even spell that right. What is left? So I want you to think about a block. I'm going to cut it into 3. Why did I cut it into 3? Because of the 3rd. And if I shade in one of those blocks, that's 1/3, what is left? What am I left with? 2/3. That's what's left. All right, so let's now answer some questions. Question 1. What is the starting value of the car? It's given to us in the problem. The new car costs $18,000. That's how much it's cost us, or it cost this person. How much is left if I lose 1/3? Well, we just answered that question. What is left? 2/3 is left. Okay, how did I represent this? Right here. I can represent it by 2/3, or I can go 1 minus 1/3, which is equal to 2/3. All right. So we talked about in class, if a buyer worries that his car will be worth nothing, a lot of you said, no, I don't agree with that. Because, it just doesn't make sense, right? And you are absolutely correct. All right, but now let's fill in a table proving that it makes sense. Remember what I said. We started with $18,000. This is in year 0. This is when I bought the car. How much is remaining? How much is remaining? 2/3. So we're going to take 18,000 and I'm going to multiply that by 2/3. Okay, that's in year 1. Well, now remember, every year I have to multiply it by another 2/3. So if I were to use a calculator right now, my calculator I'd put in 18,000 and I would multiply that by 2/3. So what do I plug into the calculator? 18,000. Then I'm going to use parentheses and I'm going to go 2 divided by 3. Close my parentheses because that's 2/3. And when I do that, I get $12,000. I can keep doing that. I can take 18,000 and now I've got to take away another, I've got to multiply again by 2/3. Because remember, every year I have 2/3 remaining from the previous year. So what is 18,000 times 2/3 times 2/3? 8,000. I can keep going. Do you see a pattern here? What am I going to write next? 18,000 times 2/3 times 2/3 times 2/3 after year 3. Because again, every year, are you noticing the number of times that I'm multiplying? 2/3 is the year for 2, for 1. Do you know that I could actually write this using an exponent of 18,000 times 2/3 raised to the power of 3? And when I do that, I get, if I'd have to do it one more time, 18,000 times 2/3 times 2/3 times 2/3 again. And when I do that, I get $5,333.33. That's for year 3. I can keep going. But it just takes too much time, right? I mean, I could keep filling in the table. And I just keep following the pattern. So this very last cell down here, right here for year 6, would look like this. 18,000 times 2/3 raised to the power of 6. Because if not, I'd have to write out 2/3 6 times. And Mrs. Hennefarth is just way too lazy to do that. And plus, I'd run out of room, right? So what we're doing is, this is decay. It's decay because my multiplier, my factor, is a fraction. That's why it is decaying. Remember, for my, when it got bigger, look back here. When it got bigger, remember my multiplier was 2 in this case. In this case, my multiplier is 2/3. So let's keep going. Now, what happens if I want to write an expression to show the value of the car after each year? Well, think about it. What did I start with? How much money was my car? It was 18,000, right? And how much was left each time? 2/3. It's always what I'm left with. What is left? What is remaining? And now the exponent just goes right up there. In this case, instead of x, I'm going to put t. Now it says, let's write an equation. Remember, this is an expression. I know it's an expression because there's no equal sign there. So now I'm going to write an equation. So now I'm going to do an equation relating the value. So that means V, the value of my vehicle, is going to be 18,000 times 2/3 raised to the power of t. T represents the years, the time, the years. How many years have I owned the car? How am I going to be able to figure out what its value is after 10 years? Well, if that's the case, if I want to know what is it after 10 years, I'm going to plug in 10 right there for t. But now it's asking us, let's find the value when t is 0. So I want to know what is V if I were to go 18,000 times 2/3 raised to the 0 power. So I'm hoping you remember. Oh, Mrs. Hennefarth, I remember anything raised to the 0 power, anything at all, is 1. Therefore, what is 18,000 times 1 is simply the value is 18,000. And I want you to think about, what does that mean? Go back to our table. Take a look. It's what we started with. Take a look. It's what the new car cost me. It's the initial value. All right. The last piece is now I've got this new situation right here. A different car. This car lost money at a different rate. Here's an equation. I'm given this equation of D is equal to 10,000 times 4/5 raised to the value of T. We're supposed to explain, what does 10,000 and 4/5 mean? Well, I'm hoping you're yelling at the computer now and say, Miss Hennefarth, I know 10,000 is how much the car was worth originally. This is what I paid for it. The original cost me $10,000. And I'm hoping you are screaming at the computer telling me that 4/5 was remaining after every year. In other words, the decay rate was 1/5. So it decayed 1/5, but 4/5 was remaining every year. All right, I hope that helped. Hoped it solidified a little bit more. Deep dive into this lesson.